working as a application engineers. So going to start our discussion. Today I'm going to present on high power density AC to DC adapter design using QR flyback converter. In this, what you expect from these sessions. So basically, after going through these sessions, you will get familiar with what is USB PD, what is USB PD adapter market with the perspective of which in what is the range of the output power, which topology is dominating the market, or which topology is being preferred presently in the market. And then going forward, we will get introduced to the basics of the flyback converters, in which I will explain what the basic working of the flyback converter, including its operational modes. And then we will go to the further what bit ample comparison between multiple topologies which are used for the USB PD adapter applications. And then we will cover why QR flyback converter is being preferred topology, what are its pros and cons, and then we will go into the detail of the QR flyback converter working along with its control law. Then we'll come back to next topic, what are the design challenges which generally in practical situation faced, then what is the solutions, and in that perspective we'll come to the world first technology, oxless biasing, self oxless biasing GAN integrated QR flyback converter, which have a part number UCZ28826. And then we will go through the design examples, in which I will show you the 65-watt single port as well as dual port designs. Before that, going into the brief, we will see some features which are necessary, such as X-cap discharge. There are more topics, but particularly I would like to highlight on the X-cap discharge with safety perspective. And then we will go into the detail, what is the design flow for one's adapter design, in which I have here two reference design. One is UCZ 28826 EVM-093, which is a single port max 65-watt power design. Another one is PMP 4117 dual port design. And both design is available at the ti.com, which you can Google and get to know about it. Going forward, let's start our presentations. Am I audible to everyone very properly? Can anyone confirm?
Yes, you are audible properly.
Okay. Suddenly I'm hearing some background noise. I was not aware of it. Please,
No,
if
it's
any distraction, let
properly
me know.
audible.
Okay. Thank you, ma'am. So in the first things, we will see that what is USB PD. So USB PD is basically our PD controller adapter chargers. This is a kind of standard. So if we see that in a very long back, we are in the range of very low power, 2.5 watt. Then we went to 4.5 watt for some time durations, and then we went into 7.5 watt. But after that, for certain long time till now, we are maximum of our charges are in 65-watt 45-watt range. Then USB PD standard increase up to 100-watt, and then at present it's up to 240-watt. So in this power range category, there are different USB PD standards such as USB PD 2.0, USB PD 3.0, 3.1, as well as USB BC 1.0. So this table is representing what are the maximum voltage and maximum current, and hence maximum power this USB PD standard represent. For example, at present, currently dominating are the last two one, which is USB PD 3.0, USB PD 3.1, which have USB 3.0 have a max output voltage 20 volt and 5 ampere, thus max output power of 100 watt. But in this it's a max power. So when you will purchase the adapters, or if you read its specifications, you will see the output voltage such as 5 volt, 9 volt, 15 volt, 20 volt, slash 3 ampere and 3.25 ampere. So for 5 volt, 9 volt, 15 volt, it supports the current till 3 ampere, and above that for 20 volt and 3.25 ampere, that's how you will get our 65-watt adapter charges. Some adapter charges, including the dual port, you will see that for 20 volt, it's supporting 5 ampere, and thus it can support 100-watt charges, 100-watt maximum output power. In USB PD 3.1, the output voltage max is 48 volt, but it is like this: 5 volt, 9 volt, 15, 20, 28, and then 48 volt. So for each, these are the max values, but in between you have the range of the values which are standard values. And for the same, I have another charts which to show. So next thing is that we have seen the type C, basically, which we use in our phone, and if we connect either way, we get still it's work and it charge our phones. The reason is it have the replicated circuitry in the both side, and this is called USB PD receptacle. So what I was earlier talking about, these are the max ratings, and then is still you have multiple voltage range which are 5, 9, 15, 20. With respect to power, what are the voltage and current, you combination of voltage and current can be used is highlighted here. So for example, if I take in the range of 45 watt to 60 watt, we can see here it can support the current of 2.25 ampere into 20 volt, and then all the way it can go up to 5 ampere 20 volt, which means we able to get the 100-watt output power. So this is all about this slide. If anyone have a question, please feel free to stop and ask in between. If any question, please do let me know, or else I will then move forward.
Okay, you move forward. Later you'll ask. Okay.
Okay, sir. Then second slide is all about with respect to topology, which topology is getting dominated at present in the industry. We can see from the chart that 87% is getting dominated by the QR flyback, and then 8% is getting dominated by LLC, and the 5% is getting dominated by active clamp flyback. And here is one more thing I would like to highlight, that there is a new topology which is being introduced within the market, that is called AHB, asymmetric half bridge topology, and it is also gaining the market within this 8 and 5%. So this percentage will get redistributed, but at present it just got introduced, not that much have a market. It's just like a start point for the AHB. Now, with respect to power level, as from the previous slide, we have seen that USB PD's market max power is 240 watt, and then with from total power like 22 to 40 watt, what are the percentage of the market usually lie in which power range? So we can see from the second chart, that flow chart, it's from 20 watt to 60 watt, 69.5% of the market is in between this power range. Then 19%, 12% is in the range of 65 watt to 150 watt. 19% is in the range of 150 watt to 240 watt. And our AHB, which is new topology being introduced, is lie into this region. This is one thing. Now going forward, this is with respect to QR flyback. In USB PD market, why QR flyback is dominating? The reason is lying here. It supports you very high power density, high efficiency within this power range 20 watt to 65 watt. So it's a correlation is like that. We are saying QR a flyback dominating 87% of the market in the power range of 20 to 65 watt, which is 69% of the USBPD power level. So here is a one short comparison that for this, let's say I have a 45-watt charger which used to be this big, but with the current trend and technology and concepts, we are able to achieve a very high compact, high power density adapters. So there are multiple more chargers for like singles, very compact single port charger, compact as well as multiple port chargers. Now, apart from the chargers, where do the QR flyback is being used? Apart from these USB PD applications, so they goes into the very high advanced electrical sockets, laptop chargers, as well as home appliances. Now, coming back to what is the flyback converter. So flyback converter is a switch mode converter basically for the end application DC to DC or AC to DC applications, and it have a transformer in between. Transformers, or some people use the terminology called couple inductor. So what happened during the FIT turn off, energy get transferred from primary to secondary, and the FIT is turned on. That time energy get stored into the transformer. Just a basics, as we have the transformer here, so it allows us to provide isolations. So the first question we should ask, why we need isolations. So there are the if we see in our home, we have a universal AC line which is 230 volt AC 50 hertz. So if we see it's in the DC terms, it will be root 2 times, which means almost 325 volt DC, which will appear at this cap C in, and we all the way our charger which have the output specification is standard 5 9 15 20, which means we are like directly stepping down from 325 volt to 5 volt minimum voltage. So there are, when you design the board in a very compact form, then there is a clearance needed in between to maintain the required industry specs. So here flyback topology give a very good edge with that perspective. Also, it can support a wide input and output voltage range, and the output can be even higher or lower with respect to its input voltage, as well as I discussed just 1 2 minute before that, we can step very high voltage to very low voltage. That's how next point is high conversion ratio possible because of the transformer turns ratio. It depends what the input and output we want, and we have the flexibility to design our turns ratio accordingly. And the next point is it's give the low cost. This is with the perspective that if we are having the same applications, same power level, and we are trying to utilize different topology, for example, LLC, ZVS flyback, ACF flyback, QR flyback, then which topology will give you the advantage. So in that terms, it's a flyback. It have a lower number of count of component, thus it reduce your cost. And as we have the flyback transformer here, it's able to support the multiple output. Now coming to its working principle. So what happened? We can divide it into the three. Yes, sir. Any question? Hi, someone is speaking. I'm not able to hear properly.
Actually, background forgotten to mute. Actually, you please carry on. Okay.
Okay, okay. Sorry. Okay, so we can divide here well, let's say we are talking about the one cycle period, and we can divide the time period into the three segment: on time, commutation time, and off time. So what happened during the on time? On time, we are talking with respect to the primary side fit. When this fit get turned on, ideally, let's say the voltage drop across this is zero. Practically, it will be I into R, the current flowing into the drain of this fit into the RDS on of this FET. That voltage drop. So what happened? Our input voltage will get appear across this FET, and I will just. So here we will get the polarity like plus and minus. So and as it have a reverse polarity, here you will get plus minus. So this diode get reverse bias. Thus no transfer of energy happen from primary to secondary. However, this energy get stored into the magnetizing inductance of this transformer. And then we go to the second slide where it's a commutation. time, a commutation time. So basically what happened before turning on the secondary side, so they say there we have the magnetizing inductance, and at this node we will get the total cap. This is the basically sum of the parasitic cap of this FET, parasitic cap of the transformer, and the parasitic caps due to any reason formed onto your PCB board. So the total switch node cap get form an LC tank along with the leakage inductance of this transformer, and thus start oscillating. So what happened because of that, as let's suppose if I say my FET is rated for 800 volt, and if the LC will start oscillating, it can go all the way higher plus minus and may cross 800 volt. So if it goes above 800 volt, say 1000 volt, then this FET will get damaged. To prevent from that, what the concept of clamping came into the pictures. And here the for the clamp there are different kind of circuitry used, but in generally very preferable is the RCD snubber used. So during the commutation time, what happened, the amount of energy stored into the leakage inductance of this transformer get dissipated across the this clamp circuit. Particularly if I'm talking about RCD snubber circuit, then it got dissipated across the snubber resistor. And once this start building up, the moment it reaches the output voltage of V in plus uh, V in by N plus V out, then this secondary actually what happened here, the magnetizing inductance get charged fully, and if the polarity across this is get reversed, and thus the in the thus what happened, this become forward bias, and the energy from primary to secondary start getting transfer. And in the previous time, when FET is turned on, that time there is no transfer of the energy, but as we are explaining this with the assumption that it's in steady state, so this time output cap stored energy into the output cap supply the energy to the load current. And same goes in during the commutation time. And in the last, when the off duration, when the FET is turned off and the polarity across the inductor get flipped, and hence your secondary side diode start uh, conducting, or we can say get forward bias. So output cap charged again at the same time also pump the energy to the load. So this is the very basics about the working of the flyback converter. We will move ahead and we'll go into the operation modes of the flyback converter. So we might have came across these terms CCM, DCM and QR flyback, and sometime valley switching too. So in CCM what happened, if I explain it in a very simple manner, so in the first, in the slide number page number 6, as I said, the first energy get stored into the transformer, then it get when the FET become turn off, then it get transferred to the secondary side. So in CCM what happened, when the FET is turned off, energy start transferring to the secondary side. Before it get completely transferred, again the primary side FET start conducting. That's what called continuous conduction mode of operation. If it goes into the waveform, here VGS represent the PWM control signals, VDS represent the voltage across the switch node, this V drain from this node to the ground, and then current waveform there shows how much current flowing into this and this. So we can see that here again our here we have secondary side current, it's already have some offsets, it's not went fully zero as like in the second waveform. Again we got the next PWM signals and start conducting. So in CCM, it just to understand in a very simple manner, complete amount of energy stored in the transformer do not able to get transfer completely to the secondary side. So due to this, what happened? We have a low conduction loss as the I peak goes low. A delta I peak value is low as compared to the DCM, QR, and valley. But switching frequency become very high. Thus, we have a very high switching loss. Switching loss basically the half CV square into F switch, and V here we can see at the switch node it's a hard switching. So here V is very high. And generally, if we go into the real mathematics, so it become V in by N plus V out with respect to the turns ratio shown in the earlier slide. So it's a very high voltage. For example, let's say I'm switching, operating my converter at 230-volt AC. So it will be appear voltage across this bulk cap will be 230 into root 2, which means 325 volt. And let's say output voltage is 20 volt and the turns ratio is 6. So you will ended up with 325 plus 6 into 20. So you reached almost here 320, very high voltage, and thus it's hard switch, and you ended up with the high switching loss. Now coming to the DCM, in DCM is the discontinuous mode of operation. So what happens here, when the when the FET get turned off, the amount of energy start transferring from primary to the secondary, and once it get completely transferred, and still there is a time called DCM ring time, in which there is no transfer or store of energy happens within the converter. That's why it's called discontinuous mode of operations. Next point with respect to the switching perspective, just to identify how we can see after seeing the waveform, it's a CCM, DCM or any other. So at the edge, you will see that the current reaches it zero. Other term generally used that transformer got demagnetized here. Then after that, in any number of valley, it can again start the switching depend upon the control law. And in DCM 2, it's separate from QR flyback. As you might see, both waveform look kind of similar. In DCM, it can switch it here also, here, which means it can switch at any point of the valley, in the ring, not valley. Apart from valley, it can switch at any locations and thus have a high conduction loss. And as it's going to the DCM ring, thus our off time duration increased. Let's say even on time is same. So overall free switching frequency reduced, thus have lower switching frequency and lower switching losses. Now coming to the QR flyback. QR flyback. So in QR flyback, first to QR stand for quasi resonant, and QR term is generally used for the first valley switching. If I say valley switching, it means it can switch in second valley, first valley, second valley, third valley, fourth valley, or n number of valley. But QR term preferably used or technically designed for the first valley switching. So here what happened, once the energy transfer from primary to secondary, when the transformer get demagnetized, after that, whenever the first valley came, immediately controller give the pulse width and turn on the FET. So first valley operation happen here. That's why it's called QR mode of operations. And it have a good trade-off between the conduction and switching losses, because it's the in QR flyback, if we go through the control law, which we'll see in the upcoming slides, that there is a trade-off between the switching frequency as well as the peak current. So in the other terms, we can say that the control law is the combination of the peak current control as well as variable switching frequency control. So there is a good balance between the conduction and switching losses. Now, going toward the ample-to-ample comparison with respect to USB PD, what topologies are used and why they are used. So first is QR flyback. It's a very basic flyback topology, have a minimum component with respect to other. Very good choice for the wide input and output voltage range. But here the disadvantage is that leakage energy get dissipated across the snubber resistors. So this is the circuit I was talking about, the RCD snubber. So across this snubber resistor, the leakage energy get dissipated. Thus, that is a disadvantage, and it's two value switchings. And Next, coming to the active clamp flyback. So this is also a basic flyback topology, but as the leakage energy is getting wasted here, the same leakage energy get recycled back within the topology and then transfer back to the secondary. That's why it's called active clamp flyback. And it's also give the zero voltage switchings, have a high switching frequency, good for wide input on output, but have a more component count, give better performance, but also at the cost, thus have higher cost. Now coming to the asymmetric half bridge, this is the new something which came into the market. First is so if we see in the primary side, it's similar to the flyback, but in the secondary side, it is similar to the LLC converter. So it's a combination of basically flyback plus LLC. I will not go so much deep into this topology, as our main motto is to discuss about QR flyback. So this topology also recycle leakage energy, provide Z-wave switching, high switching frequency, less voltage stress, good for narrow input, as well as have more component count with respect to QR flyback, but also give better performance as like a ACF at the cost. Then coming to the LLC converter, here the topology shown is the half-bridge LLC converter. It utilizes this leakage energy. This is basically the LR leakage inductance, and it helps in achieving the ZVS and ZCS switching. Also have a high switching frequency, high power density. It's very good and lower the EMI, both with respect to conducted EMI and radiated EMI, and easily achievable efficiencies more than 95%. Here, one more things which I would like to highlight is that we have seen the topology comparison that less than 75 watt QR flyback and ACF are preferred topology. Greater than 75 watt AHB as well as LLC converter is preferred topology. But there is a catch that it's a industry standard that if we have a output power greater than 75 watt, then there is a need of the PFC, power factor correction circuit. So very slight basics about the PFC here. It's a boost derived topology that saves the input voltage with its it saves the voltage with its current and thus have power factor of 1. Often required to comply with the standards plus 75 watt output power. It need PFC and mitigate the effect of the complex loads. So if we have the power level greater than 75 watt and AC to DC converter, so there will be kind of two stage AC to DC plus DC to DC, and thus PFC is known as a pre-regulator for such kind of applications. Input range generally depends upon the region plus application types. For example, in India, we use 230 volt AC 50 hertz, but in Japan or in European standard, we use 115 volt AC and 60 hertz. So input range depends upon the application and its type as well as region. Most of the PFC use diode bridge rectifier. As is shown here with a single input instead of three-phase input, and the typical output of the PFC is in generally 390 volt DC or 400 volt DC. It reduces the stress on the energy infrastructure by maximizing the power and minimizing the TSD. So if we just to quickly go through these three waveforms. So here what happened with a very purely resistive load, voltage and current are in phase. And with a purely inductive load, voltage lags the current by 90 degree. With purely capacitive loads, voltage lead the current by 90 degree. So, uh, but at the end, we want this kind of waveforms which help us to minimize the reactive power. Here is one of the analogy given, but I think most of the people are familiar, so I will skip this part and will go forward. Here is the summary of the last 2 to 3 slides and showing the comparison. Just quickly, we can go through for the QR flyback. What is the advantage, pros? It provide lower cost solutions, have higher efficiency, and it's a give good trade-off between the efficiency and cost. It's a simplified design, whereas ACF, recycle the leakage energy, have high switching frequency. LLC gives soft switching, high switching, and high switching frequency. Talking about the disadvantage, so snubber loss is dominant in QR flyback, and it by default give the GVS at a low line, but there is a no GVS at a high line, which becomes which give you higher switching loss actually. So coming to ACF, higher bomb versus QR flyback, there is always a struggle on that side. Then higher SR MOSFET VDS compared to the AHP, as well as QR flyback, and the LLC narrow output voltage need PFC as front end, challenging magnetics design. With respect to efficiency, these are numbers like minimum efficiency achievable, peak efficiency can be higher than these numbers. So here 230 volt and 115 volt, we call it high line and low line. So with at high line 92.5%, low line 92%, high line 94% and 93.5%, and LLC have a higher efficiency. But when it comes to the cost, the QR flyback give you the lowest cost, while ACF and LLC have the high cost. With respect to power level, up to 100 watt, QR flyback is the preferred topology. Greater than 100 watt till 240 watt, ACF as well as LLC is the preferred topology, and all of three have a high power density. But if we do the trade-off between its cost, complexity, simplified design, power density, efficiency, so QR flyback is the preferred choice. We'll go into the detailed working of the QR flyback here. So this is the basic circuit of the flyback. So what happened, as explained earlier, when the FET turns on, then energy get stored into the magnetizing inductance of this transformer, and when the FET turned off, the stored energy into the magnetizing transformers start circulating to the output cap, and thus charge the output cap and supports the load requirement. Here showing again going into the working, main target is not to is to go explain how the switch node waveform look like. So here I'm showing the waveforms which is operating in the valley number 4. So if we go mathematically, so it's always half of this valley always sits V input voltage. Then this ringing from here to here is NV out either side, and thus the plateau voltage for the this switch node is V out into NP by NS plus V in. So when we design our QR flyback, so the FET ratings need to be higher than this voltage, and voltage above this basically called overshoot voltage, and this overshoot voltage plus V out into NPS determine the capacitor rating of this clamp capacitor. So here are two types of ringing we can see. First is this one, second is this one. So this ringing is generally come from the leakage inductance as well uh, switch node caps. Leakage energy is generally in the flyback need to be 3% of magnetizing inductance. So if I say that I have a 200 microhenry inductance, magnetizing inductance, then it's a 3% is 6 microhenry. And even if I have a parasitic caps, which is just let's say 100 picofarad, so we will ended up with almost 1.6 megahertz frequency here. So it's a very fast oscillating. Sorry. Ma'am, can you repeat? I'm not able to hear you properly. Is there any question? Okay. So this is the high frequency oscillations, and the second oscillations is due to the magnetizing inductance and the parasitic nodes. Thus, and the magnetizing inductance is the high value, let's say 200 microhenry into this. So its switching frequency is less as compared to this. This is generally in kilohertz range and this is in megahertz range. So at the DCM means this point, a magnetizing inductor resonate with the switch node cap. Basically, talking about this valley. Switching at valley reduces the switching losses. So basically, what happened is on time is, let's say, fixed, and if I switch in first valley, then my total time reduce, which means I'm operating at very high frequency. Further, if I go to second, off time increased, switching frequency reduced. So the number of higher valley is the converter operating ended up with the lower switching frequency. Thus helps to reduce the switching losses, as well as there is a trade-off between the peak current and variable switching frequency. So also reduce the conduction losses. Thus, its QR flyback helps to achieve a higher efficiency. At a low line, what happened? This V out into NP by NS plus VEN. So this comes down, and by default this voltage reach almost very close to the zero. That's how by default it gives GVS operation at the low line, but at a high line it's not achievable. It's the same waveform. Another thing just to show with respect to power level, the moment we start going to the higher power, switching frequency start decreasing and we can see it's all the way come to the 100 kilohertz. This is the industry preferred kind of range for the higher power applications, higher output power. They generally prefer 100 to 200 kilohertz switching frequencies, and the peak current demand all peak current almost going to the 2 ampere, more than 2 ampere, less than to 5 ampere. So blue curve is for peak current. Now coming to the control law for the QR flyback. So control law here is the combination of the peak current control as well as variable switching frequency control. And based upon its feedback pin voltage, its operating point changes. So here if I say, if we go through the table, so with respect to the loading and the feed FB pin voltage, it operates in different mode of operation. So here, this is the control law shown for the UCC 28826, or in general, QR flyback. It's also kind of same. So if we see, we are if are at a very tiny load, then we are operating into the burst mode operation. Then if we go to the lighter load, it will goes into the frequency foldback operation. Then with increase in load, but still light load, it goes to the sixth valley. Light load to heavy load is like all the way goes from sixth valley to the first valley. And for the heavy load, particularly it's low line and full power, it's operate in the first valley, QR with the frequency clamp. And for the peak power demand, it goes into the cesium. So here is the EpiPen. We are sensing here is step it down, and then we have our compensation circuit, and here optocoupler used here. This transfer the energy from the this output secondary side to the primary side. Then this EpiPen basically a kind of error amplifier output voltage, which goes to the controller and provide information if Vout is getting increased, decreased. Based upon that, it's get the information about the output power level, and thus uh, changes its operating point. So what is the first next question is, what is the burst mode? In burst mode, what's happened? By the way, I will show the details about this mode of operation in the reference design, but to give slight insight, in the burst mode, what happened that we do valley skipping. So, okay, I will use. So when our output voltage charges, it goes like this, and overall average values remains constant. So what happened at a lighter load? we don't have any load to discharge this cap so much. So it stops, skip the switchings, and just only switching will appear when this V out is discharged to charge it again to maintain the required output voltage. So that is how the value switching will only appear whenever the output cap goes low. Next, frequency foldback. The same concept here also. Then sixth, fifth, fourth, third, second valley based upon the loading. Operating point get decided based upon its feedback voltage, and thus peak power it goes into the CCM. Then here are few of the design challenges we have with respect to the adapter design particularly. Content going forward from here will be specific to the adapter design. So generally what we have to generate a VCC supply. So we have a controller, right? So what happened? We need a supply for it to work. To generate that biasing, generally what we do in the flyback transformer, we put third winding known as auxiliary winding, and then kind of we design a peak detector circuit, diode and cap, and then take the VCC cap. And the turns ratio of this is, let's say, if this VCC is directly in proportion to the V out. So what happened if, let's say, even if I say this value is Na by Ns is 3 volt, and our USB PD application have the multiple wide output range, all the way from 3.3 volt to 20 volt, 3.3 volt, 5 volt, 9 volt, 15 volt, 20 volt. So but this is the fixed value. Turns ratio is become fixed value. So what happened for 3.3 volt, you will get the VCC 10 volt, but for this 20 volt output you will get the VCC 60 volt. But our controller pins in general are not rated for such a high voltage. Thus, it may damage the controller pin. So, excessive high voltage on VCC when the voltage is high, this is the disadvantage. So, there are different traditional ways to approach to resolve this problem. So, generally, people use the after getting this voltage, they put another circuitry before going into the controller, step it down by either discrete clamp circuit or integrated linear regulator. Highlighted red circuit is the new circuit which can be used further to bring that 80 volt, 60 volt all the way to 12 volt VCC required. Next, very common or generalized circuit used is the tapped auxiliary winding. Either it's a discrete or integrated. So here, so So here what happened, let's say if I have a 5, 9, 15, 20 volt output. So for 5, 9, one circuit will, it's kind of ORing of the diode happening here. One circuit will work, and for the higher output voltage, another one will work. So here it's a regulating the VCC by using this tapped aux winding or discrete integrated circuit. Third way is after putting the aux winding, design a boost conductor itself and then get your VCC. But all these circuit have its own disadvantages, such as if I'm going for the discrete clamp circuit or linear regulator. So here I need one extra zener FET as well as the component, and this FET need to be rated for higher voltage. More if I even is coming 60 volt, there will be some ringing, so almost 80 volt NMOS you need here. And then here in the linear integrated linear regulator, we need a VCC pin to all the way to go basically this circuit linear integrated circuit. So you need a VCC pin of the controller itself to be rated for 80 volt, which is kind of not possible or have another consequences. Boost conduct boost converter if we will make, then we will ended up with having the discrete inductor, which itself size is big. So another is not preferable. Taps aux winding, this is generally used one, but have two to three disadvantages, such as first itself VCC pin need to be very high, a voltage rating, maybe 80 volt or sometimes even higher based upon the turns ratio, as well as there is a high chances of the cross regulation, poor cross regulation between these multiple output voltage, output windings. So, thus, to conclude, we ended up with having the high component count as well as cost and less efficient circuits. So here we got the first world technology, auxless biasing, high frequency auxless QR GAN flyback converter, which have a self biasing. What do I mean by here self biasing? That there is a no aux winding on the transformer and the VCC supply is getting generated inside the converter itself. Another thing here I would like to highlight is the two term I'm frequently using, converter and controller. So what happen if we have just a controller, if the only control law is integrated and at the end we are getting the PWM signals, that's called as a controller. But if the FET get integrated within the this die itself, that's called converter. So this is UCG 28826 is the converter, not the controller. So FET 700 volt, 170 milliohm RDS on, it have an integrated within the within inside. So it the feature wise, it's a have a self bias and self sensings without an aux winding or LDO. Generally, when we are using the aux binding on the transformers, the purpose is to generate the VCC binding as well as sense the output or voltage for different reasons, like if you want to implement some protections or sense to define its operating points. So those things have been become self biased and self sense. Then the FET inside have a is the 700 volt GAN FET, as also have the RDS on of 170 milliohm, very low RDS on, so good choice. And then it's a feature wise, it will have a HV startup and current sense. Mode of operation, it have CCM, QR as well as DCM, and can go up to all the way to 500 kilohertz switching frequency. So whenever we are designing any reference design, there is a trade-off between the switching frequency and size. Higher the switching frequency, lower the magnetic size, and hence ended up with a small and compact design. So this converter supports till 500 kilohertz switching frequency. This enables the less than 30 milliwatt standby power. So question is, what is standby power? Standby power is when we are connecting our circuit uh, to the supply, but load is not connected, still there are internal circuitry which taking the some drawing the some current, and thus some power loss is happening. So in that term perspective, this part provide you to achieve very less standby power, and this is a very good point. We have less than 30 milliwatts. This provide best in class efficiency with the frequency foldback and burst mode. So based upon the feedback pin voltage, it can it cannot do the value switching. So for the value switching higher than the sixth value, it can it's like it don't go into the value switching. Instead, it's go into the hard switching kind of, but at the same times it goes to the very high number of value at the end. It's like this is called value switching, and it's but instead of switching here, it's go like, sorry, it's like go like this and thus kind of this, and it starts switched here. This is called frequency foldback, and what happened with this, it reduces the switching frequency so much, thus have the give the advantage toward improving the efficiency, and also provide burst mode. It mitigate the frequency, it mitigate the EMI noise by the concept called frequency dithering, where the energy is basically spread into the spectrum such that the noise coupling get reduced within the board, or it should not get coupled back to the our main line. And have adjustable slew rate of the switching speed. and have a full sets of protection features such as over temperature protection, over voltage protection, short circuit protection, over current protection, over power protection, and brownout, and consistent overpower protection trip points meeting the LPS requirement. And these are configurable by these protection features and few more of the things like TR pin, like turns ratio, frequency, peak current. All these things are configurable by the external pins and can be set using the registers. So if we see the its application schematic on the right side, so we can see that we have HV pin, CDX, TR, FCL, IPEAK, FLT, ground, FB, feedback pin, switch node pin, and VCC pin. So here these four pin, TR, FCL, IPEAK, and FLT are configurable through the registers. Sorry, CDX, TR, FCL, and IPEAK are configurable through the register, and at the FLT pin we use the NTC to detect the over temperature, external over temperature uh, fault. Also another things you can get on this FLT pin, if any of the fault is getting triggered, it will generate a fault code on the FL on the CDX pin, which fault code, time duration, and standard things mentioned. You can go through the data sheet, it's available on ti.com, and check how it's work. Application point of view, this part can goes into the fast charger, notebook adapter, wall outlet, docking stations, audio sound bars, as well as for the all kind of high power density industrial AC to DC power supply, along with single phase industrial auxiliary supply. With respect to its benefits, what it provide you, it enables you to achieve a very high power density design. When we say very high power density design, we means density greater than 1 watt per cubic centimeter. So it's able to achieve more than 1.4, approx 1.4 watt per cubic centimeter. It's helps to simplify the system design with a fewer passive components, and also simplify the bias supply management for the wide layout application. As I discussed, if we have a aux winding and output voltage in the range from 3.3 volt to 20 volt, then you ended up with the problem on the VCC pin side. So when you go through the data sheet, you will able to get what is the max rating of this all pins. And in general, VCC controller pins are rated for very low voltages. So this UCZ 28826 has simplified this bias supply uh, issue which used to be there. So any one of you, if you want to have more idea about how this self-biasing works, or how it's implement, you can go on ti.com and search for the UCG 28826. You will get its data sheet, multiple reference design, as well as calculators, tools to start your design. Now coming back to how we do the reference design. So the flow is like this. We first define the spec. For example, here I have taken the specs: input voltage 90 volt AC to 264 volt AC, output voltage, it's a USB PD. So there is also an option with this part that we can go for the fixed layout circuit. So here I'm taking for the USB PD chargers 65 watt. So it's have the output voltages 20 volt 3.25 ampere means 65 watt, 15 volt 3 ampere means 45 watt, 9 volt 3 ampere 27 watt, 5 volt 3 ampere 15 watt output powers. So overall max output power it can support 65 watt, but also there is a trend within the industry that for the very short durations they ask for the peak power demand. So without increasing the size of the transformer with the same design which have been designed for 65 watt, we for the 4 milliseconds, it can support the peak power of the 2x rating of its max power design. So here it had been designed for 65 watt, it's able to support 130 watt peak power. So into the when we go into the design, there are few things which we need to take care. So a flow is like this. First, we define the specs, then we do the calculations, then component selections, then we do the simulation, and then we do the layout. Layout can be done by using the multiple available PCB software. Here we use the Altium software, and then we do their schematics, layout, get it reviewed. Uh, there are multiple things to be considered while the component selections, like we need to take care of the component, check what are the component with respect to its rating. That is the first thing. Then if they are preferable, like series wise, if I talk about the register selections, there are multiple standard like 0603 package, 0402 package, 1206 package, 0805 registers package. So what happen if we don't plan it properly, then it will not go well. So design flow is define your specs, do the calculations, select the component, then start your PCB design, make your schematic, do the layout. In the layout, generally with this device, we go for two-layer design. There are different customers with respect to power level. You can go for four layer design too for higher power rating, but for 65 for design we will go for two layer design. And then once you got your PCB fabricated, then you start it's validating it, all those things, and the test data I will go goes into the end. But here are few things which we can actually go through. For example, the bulk cap selections. So I'm going to talk about this capacitor, how we do the calculations, and then we will talk about the transformer selection with respect to this device particularly, or in other word, for this reference 65 for design. And then we'll talk about slightly about snubber design, and then we will go through the reference design. So bulk cap selection. So what happened as first thing here, we have defined the input line 90 volt AC to 264 volt AC. So 90 volt AC, when it get rectified, the output at this end is rectified AC line voltage. So if it have a 50 hertz, then it become this is a 10 millisecond time duration, right? So the voltage profile across this curve will appear something like this. It goes from all the way here to here. It follows the path like this basically. So when we are designing the cap, this is our first priority, to know how much we want. So bulk capacitor basically it's a filter the rectified AC line voltage and provide DC input to the flyback. So the bulk cap selections depend upon the minimum AC line. For example, if I'm saying 90 volt AC, so this value, peak value will become 90 into root 2, and which is almost close to 120 volt. If I am not wrong, though, it goes to 120 volt DC. Now we have to decide how much delta we want, how much this bulk cap input voltage go lower. Let's say if we go for 50 volt. So this is called the minimum, this 50 volt called minimum DC voltage requirement. Minimum AC input voltage is your this value, and this value is called minimum DC voltage requirement. So based upon that, we do the calculations here, just a simple math here. So let's say from here to here, your time is T. Okay, and we are trying to come from all the way to here. So you are coming from root 2 times of VAC min to the V bulk min, let's say. So V equals to Vm sine omega t. Omega will become, okay, let me write it. So this is, let's say, V1, this is V2. Root 2 times of VAC min, and this is V bulk min. So we are going, V bulk min is equals to root 2 times of VAC into sine omega t. So let me write it in the form of 2 pi ft. T, and our target is to calculate the T. So T will becomes 1 by 2 pi f into sine inverse of V bulk min divided by root 2 times of V AC min. So we got the time from here to here, and as the total line frequency is from here T line, so half will become T line by 2. From here, one cycle it will become T line by 2, and then half of that will become T line by 4. So the time total discharge time. So this is our cap in this duration. From here to here it's charging, and then again here to here it discharging. So discharge time durations is becoming 1 by 4 T line plus T. And T we calculated, then 1 by F can be written as T line by 2 pi into sine inverse of V bulk min by root 2 times of AC min. Now using the formula, input power is equals to half CV square. So basically in a simple term, you can say we have to see what amount of energy this cap can hold. So through that, we will get the bulk cap calculated in reverse. So when you do simple math, half CV square, CV1 square minus, okay, I will take half CV and F common minus V2 square into F switch. So this will become your input power. So input power is equals to output power by efficiency, and then we do the calculation for the this C, then we will end it up with this equation. So the bulk cap is can be calculated using this formula 2 into P out by efficiency into T discharge divided by root 2 AC min square minus V bulk min squares. Now, next we are moving to the transformer selection. So here I'm not talking with respect to the transformer design. Instead, we are talking with respect to how to select the transformer. Transformer selection here can be 2 to 3 parameters needed while we are selecting the transformer with respect to UCG 28826 device, as it have the GAN FET inside, which is rated for 700 volt. So, and its plateau voltage, this basically VEN plus NV out from all the way to here. So this voltage should not go above, should not go more than 560 volt. Even though you are seeing here this mentions 750 volt and 800 volt, these are the surge case or transient case, like minimal time it can support. But actually, if you go through the detail of the detail through the data sheet, you will find this number as a 560 volt. So recommended to not go above 560. So when we are doing the transformer turns selection, so what we will consider the FET rating of this and FET rating of this. If we are going for synchronous rectification, then there also we are going to use the MOSFET. Otherwise, diode. So secondary side switch as well as primary side switch. Considering the FET rating, we will decide our NP by NS. So here are the two equations for the same, which can be used to calculate the NP by NS. Now coming to the second things, which is in magnetizing inductance. So as discussed earlier, we define our specs 90 volt AC to 264 volt AC. To calculate the magnetizing inductance, we will focus on these two numbers. Maximum output is 12 volt, 20 volt, and maximum input is 264 volt AC, which means 264 into root 2, 375 volt DC. And the maximum power it can support 665 watt. So here, when we are at the minimum bulk voltage means I'm talking about this voltage, this point, and full load. At this point, I want to support 65 watt power. Then next consideration is at the minimum input, full power, it can operate in first valley, as we can see here. With this assumption, we calculate the magnetizing inductance with the maximum peak current and minimum switching frequency. So when pre-consideration with this, first we will simply use for the on time V equals to LDI by dt. Then from there we will calculate dt. So here is directly written I peak max because current is going all the way from 0 to its max value. So V equals to LDI by dt, and V voltage appear during the FET turn on is input voltage. So V bulk min, you got your primary time. And then if we go to the second equation, and then when the secondary side FET will conduct, then voltage appear across the across the transformer winding will be V out mag NV out. So based upon that, we will calculate secondary time. And then for the third time, which is basically ring time, we can assume here 750 kilohertz as a ring time, and then half of that will become our DCM time. And we do the calculation for the magnetizing inductance. And the final equation will be input power again instead of half CV square for the capacitor calculation. Here we will use half L I peak IE square into F switch. So now we know that our switching frequency, minimum switching frequency can be calculated using these three equations. And once we get this, and through this V equals to LDI by dt, we also know our current. Or if you go through the device dataset, this is the max current selection. So we have three options: 2.8 ampere, 3.1 ampere, and 3.5 ampere. So based upon your requirement, this I will get fixed, and you know what output power and efficiency is you are targeting for. Then this will become input power is equals to P out by efficiency. Now we have our P out, we have efficiency number, L need to be calculate, we have I, and we have FSH. So apart from L, all the parameters are known. Thus, we will able to calculate the magnetizing inductance. Now, next things where we are going to discuss on the snubber design. So this is the voltage across the this switch node, and when the FET get turned off, then this form the LC resonant. Basically, this cap here we have magnetizing inductance. So this form the LC resonant, and it start resonating, and it can go very high value. It's like go like this and come back. So what we do here, we clamp it here, and the clamping done by the snubber. The moment the voltage across this FET become equals to V in plus NV out. Sorry, let's talk with respect to the previous circuit only, and there we have NV is to NS, and this let's consider that as a N. So the moment we can up V in plus NV out, the moment we pose the voltage higher than this value, V in plus NV out, this diode will get forward bias, and the leakage energy start getting dissipated across this. And the voltage rating of this cap is get selected by how much overshoot still you are allowing for short duration, minus here if it's happening the value switching, so NV out. So the snubber voltage V clamp become equals to NV out plus is overshoot allowed after this. So if I want to show you the waveform, so we can go to the previous slide. So we can see that this is the overshoot, 560 to 700 volt. So we are seeing here almost 140 volt is allowed to get overshoot, right? 140 volt. So this is basically the overshoot voltage. And from here to here, It's a half, it's always from 0 to here, this is your input voltage, and then from here to here is NV out, and then from here to here is your V out overshoot. So this is how we do the calculations. Then energy stored in the leakage energy, how we do the calculation coming to that point. So energy stored in the leakage inductance, again that will be equals to half L I square into switch frequency. So this switching frequency will be the same what we calculated initially in the earlier slide. And then L is here leakage inductance. If we know our magnetizing inductance, so leakage inductance is basically max 3% of the LM. So we know L, we know I, as we can decide which max I peak we want, we know switching frequency. So we calculate the snubber power, total, leakage power. So what amount of the power will get energy will get stored inside the leakage? We can calculate it. Then we do an snubber power. What amount of energy we want to get dissipated across these resistors is basically some arbitrary number 1.32 2 volt of this snubber power, leakage power. So and using this is equals to V clamp, this voltage V clamp chi square divided by R. So once you know the R, V, you know the snubber power, then you can calculate your R. And another thing, calculation for CSN is equals to C dV by dt. I equals to C dV by dt, and thus leakage current, basically primary side current we utilize to calculate the CSN. So to have a very better efficient design with perspective of the efficiency and the thermal, it's very important to design the transformer which have the leakage energy as minimum as possible. It would be very good if we able to achieve 1% leakage of its magnetizing inductance. So that will give you a very good edge over the others design. So what happen, lesser the leakage, uh, more less amount of energy will get wasted. That is the first thing. Second thing, what happen at a higher power and minimum input voltage, this ringing keep on increasing. So if higher this ringing, your chances of damaging the FET is very high. So it would be recommended to have a transformer which have a leakage inductance approx close to the 1%. Now moving to the next, this is a kind of features for the USB PD application adapters. So particularly talking with respect to UCG 28826 QR flyback converter, which we are discussing. So this have HV escape discharge circuit integrated inside. You can go through its block diagram in its data sheet. I will provide the link. So here we are using two diode before the bridge rectifier, and it's going to connect the HV node. HV basically here also start for the high voltage startup. High voltage startup you can understand in the perspective that when we do the first power up, how our device get waked up, how is first power up happen. So the first power up is always HV started happen, and the rest of these converters start working, and then your VCC generated, all those internal process happens. And so this HV pin helps in the escape discharge as well as the high voltage startup. So what it do to discharge the escape? Basically, it sends the zero crossing of the line voltage, and thus based upon that it discharge the cap. Zero crossing means this point. What is escape discharge standard? Basically that is another question. So basically this is a kind of safety features with which is industry standard. And why this is requirement. So basically what happened when we unplug our charger, so as per this standard, it is a requirement that within less than 1 second, our voltage on the X cap is generally connected just before the bridge rectifier. If we design uh, our design, so what happened? We have some EMI filter. Let's say I have one stage EMI filter. So this is our CLC. So these are the X caps which are rated for the safety standard like X2 rated, Y2 rated. So these are a different type of capacitors which the across which the voltage within the 1 seconds need to be dropped below the 30 to 45 volt within a 1 second. And the standard is IEC 62368-1. So here is the one waveform on our reference design PMP 41117, that when we are removing the AC supply, we can see that from to here, less than 55 millisecond, it discharged completely. It went to zero
Excuse me,
volt.
ma'am.
Yes.
If it doesn't happen, like if the capacitor is not able to do that, then what will happen?
Then you will the high chances of getting shock. And if it not pass this standard, then it's not allowed to use that design, or it's not till the time you're not meeting the industry specs, you're not allowed to sell that product.
So you mean to that transients will play whenever I'll switch off or remove the charger?
Correct.
Okay, okay, ma'am.
Okay. So here we can see that it's almost coming to 0 volt within a less than 55 millisecond. And the X cap used here is 330 nanofarad. And the waveform from where I have taken will go to the detail in the next slides. Any more question before I go into the reference design? I will deep dive into from now onwards in with respect to design. Any questions so far?
Is there any
Ma'am,
question from the person? Yes. Yes, please carry on. Any questions from the participant then? Okay, I think no question. So please carry
Okay.
on.
Okay. I hope that given you a good insight so that uh, till now, whatever we have gone through, we will
excuse me, ma'am.
see.
One question.
Yes.
Ma'am, the PD controller you had that near the output. Can you
Mm-hmm.
go back to the site? Yeah, the backs. Ma'am, the
Yes.
USB PD controller.
Yes.
Uh, what? How kind? Like what kind of feedback is there? Like what it does?
Okay. So what it does, we send the output voltage at this node. Okay, and then here the PD controller generally use is like WT. You can go through if you get the data online. WT6636F or some different USB PD controller. So what happened? It sends the output voltage, and internally it have the reference divider. Okay, so it make the reference. It set like if the output voltage is 5 volt, 9 volt, 15, 20. Accordingly, it says set the reference here and change the output, and by providing the feedback to the this converter. So what happened here? If I go to this slide, this slide. So the same circuit here we are seeing the secondary side regulated compensation use is using TL431, right? So the same circuitry from here to here is implemented in. Okay, let me change the color. Yeah, this circuit along with the reference and error amplifier, and changing the this reference voltage along with the communication with the receptacle, all those circuitry are inside USB PD controller. And after that you have your biasing resistor here, And this RLED resistor here, basically this helps to transfer the energy from this side to this side. And thus, based upon this, whatever the feedback appeared across, that will go to the device and will help to decide its operating point. Is it clear to you now?
Got it, ma'am. Got it.
Okay, okay. Thank you. Now we will go to the so this is the first design. Actually, you can directly go on the ti.com and search it for the UCG 28826 EVM-093. This is the 65-port adapter single port charger design, and the second one is dual port PMP 41117. This is also available at ti.com. You can Google it. So this is the dual port design. So we will go through it one by one. So I have the link open already, but if so if you Google directly, you will get UCC 28826 data sheet is available here. And then when we go into its design and development section, you will find this EVM UCC 28826, and this is the board final design. So see, this is your PD controller side. Communication is happening, and this we will like actual board size is this much, and the rest of the part will get cut. So this is our input bulk capacitor. Also, okay, just to give a at board level idea how it look like. So here we give the AC supply, and this is our one stage EMI filter, and these all the way go to the input bulk cap. And here, if we will go through the schematic, here this is CLC filter at the input bulk filter also, just to suppress the EMI noise. Then output of this goes to the transformer, and if we go on the below side, these are the transformer pin. Here see RCD number circuit is sitting, and then this all the way go to the controller side. This is our UCG 288. If I zoom it, uh, I think here UCG 28826 device is sitting across peripheral, and you can see that this is a 65-watt device with very minimal number of component as compared to the as compared to the others converter available within the market. This is the optocoupler. These are your Y cap, basically safety rated caps. And then secondary side your USB PD controller circuits. This is the SR PET. This is SR PET controller, and these are the HV pin diodes are sitting here. So circuit I will show. Then you can go through the its documentation. You will find its user guide. In the user guide, you will see the detailed test reports for this board, and all the safety measurements have been written. So please, if you are anyone planning to use it or evaluate it, go through its safety measures first if needed. This is how at the end it's look like. This is the 65-watt charger with the almost if 1.54 watt, yeah, 2.8 watt per cubic centimeter. So this is a very compact design. So this is how it's look like. And then we define its specs. What is the specification for this? So we can see that what are the specs needed as a input to get your design started. So first we will have the line input voltage, and then line frequency. What is your standby power requirement? What is the output characteristics? Multiple output, power level current. All the specs are defined. And then once you got your specs, you do the calculation part. You can get the I can go through its data sheet. When you go in, So from here you can directly go to its application implementation. From here you will get all the formula used uh, to get it start. Once the calculation is done, then you can make your PCB design. This design have been done using the Altium software. You can use whatever you prefer. And then once you got your board, then we start the testing. So this is the one reference design. What are the tests we need to do and how to do? So to go into the detail, I will go through the second reference design, which one is the PMP41, PMP411117. So this is the 65-watt dual port USB PD charger with this UCG 28826 cell bus GAN. And here videos is also available. You can go and you can see that this is 2.3 watt per cubic centimeter of power it can support. And the dual port means this is what it look like. Compact design. This is basically the circuitry which is inside your adapter case. This is open one. To go into the detail, I will go through the schematic first. In the design product files, you can get all the files needed. Here, it's a Gerber file is each and everything is available. Assembly drawing file, BOM, CAD, Gerber files, PCB layout, schematic. So I have the schematic already open. So we'll quickly go through the schematic. How does it look like? So we have go through its test report. What are the specs defined for this one? So this is the specs. This design have been made for 90 volt AC to 64 volt AC. Input voltage range, line frequency all the way from 47 hertz to 60 hertz, which means it's compatible all over the world. Then output spec is 5 volt 3 ampere, means 15 watt, 9 volt 3 ampere means 27 watt, 15 volt 3 ampere means 45 watt, 20 volt 3 ampere means 60 watt. This is for this. You can draw the power either from port 1 or port 2. The next port output portfolio like the sum of the two powers. So in the end, we can see that this is supporting maximum 65 watt. So by like in the single port, you can max take 60 watt, but with the addition of two port, you can take the 65 watt. Now going into the calculation part, I'm skipping. You can refer its data sheet and do the calculation, but we will quickly go through what it's look like in the schematics. So here we are giving the line and then using the line fuse. So the fuse is rated for 3.15 ampere. Most probably this design had been rated for 3 amperes. So that's how you are ended up with 3.15 ampere fuse. And then this is the X cap. This is the common mode choke. Then after that, AMI filter stays. We went into the bridge rectifier. This is a single diode bridge rectifier used here, and then CLC filter used here. CLC bulk cap. Instead of directly having the bulk cap, we total 100 microfarad divided into multiple cap to reduce the size. We are having CLC in order to suppress the noise such that whatever the switching happening this side should not get coupled back to the line. Then this is our snubber circuit, R1C3, and you can see here whatever I have discussed so far. But apart from that, there is a one uh, R3, R17 is the additional component. So when we put the resistor in series with the diode, this helps to basically damp the noise, damp the ringing further. Then this is the transformer. Transformer here used is ATQ23 series, and these are the output capacitors. And here we are going for the SR FET, and in the SR FET, and this is the SR FET controller. So in this design, we have the two options. First, to utilize the fixed V out, or else you can disable this particular circuit and take this feedback, this yellow feedback, and go all the way to its PD controller. So this feedback came, and here the PD controller communications, all those circuits. Next slides. Next schematics. And from this, still this part will be the common R10, R9, R10, R14. This is the common part, and we'll go to the optocoupler. Based upon the output voltage and the reference voltage here, the voltage at this cathode of the optocoupler, the amount of energy transfer when this LED get forward bias, you will get your feedback voltage, and based upon the feedback voltage, converter will decide its operating point. And coming to the converter side, there is all the pin. You can see HV pin is connected to the diode, and switch node is as the FET 700 volt FET is integrated inside. So this is directly connecting to the switch node, and then there is a clearance between this, and this device is QFN package. FLT pin, we have the NTC, negative temperature coefficient registers, so we can configure it according to the at what temperature, means if in the design what are the peripheral temperature, if it reaches let's say 100 degree, 105 degree, accordingly we can design the value of this resistor. Then we have the TR pin. Basically, if the turns ratio here is 6, then you can corresponding there is a register stable in the, if I go through the data sheet, we can find. So we have all the registers values across corresponding to its turns ratio. So if we have a turns ratio of 6, you can configure your registers to 5.23 kilo ohm. And similarly for IPIC, CDX and CDX pin. So if we go through here, so it's define what the functions you want, like what the IPIC turns ratio you want, configure your pin register accordingly. And in the peak current, what is the min max ratio, what is the EMI dithering depth you want, and then what is the max frequency you want. Those all things are configurable there. And also if your device goes into the lab fault. So there are basically two things happen. Once the fault appeared and your adapter got completely shut down. Second thing, some fault happen and your device trigger your protection, and then after 1 second it goes into the auto retry mode. So all those options are available and it is configurable through the sub pin register. You can select it accordingly. Then there is a third pin called CDX pin, and it basically what you want your CCM operation enable, disable, switch node turns, slew rate, basically when it goes voltage goes on, goes high or come down, what is the slew rate. Basically when it goes high, turn on slew rate, you can decide. XCAP function, if you want to enable or disable, accordingly you can decide your CDX pin registers. And so here accordingly all the register is selected, then VCC is getting generated inside, and this pin cap just uh, it's preferred to use the X7R series capacitors because those are rated for 150 degree 125 degrees Celsius temperature if I'm not wrong. So value of the cap directly preferred in the range from 10 microfarad to all the way to 47 microfarad on the VCC pin. And these two are your diode, Schottky standard diode used and directly connecting to the HV pin and acting as a full bridge rectifier. So this is your power stage. If I will classify, so from here to here. So from here to here, it comes as a power stage. And from here to here, this is called your feedback stage. And then this is the, I will not go into the detail because this is not my domain. How it's working, I do not have that much clear understanding on this side. But at the block level, we know that this set your reference voltage as per your output voltage requirement and do the communication with the USB PD receptacles. Now coming back to the test report, once we get our board into the hand, then what are the procedures, all the safety things, everything is mentioned, it's in user guide. If someone trying to evaluate, I'm saying it, please consider all the safety requirement because these are the high voltage boards. So once we get our design done, there are set of tests which we need to do to validate our design and pass those specs as a industry level. So first thing, we do the efficiency test. So as per the standard, there are efficiency specs like at 0%, 10%, 25%, 50%, 75%, 100%. What are the efficiency requirement? You need to pass those specs, and efficiency measurement you can do through the using the power analyzer at input and output side. So what we do, if I show you the board, this is the input side. So here we connect the, when we are connecting the supply, we directly connect the input power analyzer. And similarly, output side also, you connect the power analyzer, you will get your input power, output power, and thus output power by input power will give you the efficiency measurement. And then this is showing you the low line, 115 low line, high line efficiency, and you can see that the peak efficiency all the way going till 93%. So different, you can go through the test report. I would just simply go through the few points which as a university level we are not familiar most of the time. So apart from the efficiency, next come things come as the voltage regulations. What does the voltage regulation mean? So voltage regulations means when we are whatever the change in the load, if I plot the I versus V versus I, whatever the change in the output current, our output voltage need to be the constant. This is called voltage regulation. Then load regulation basically it called. And the second thing called line regulations. So in the line regulation, what happened? Whatever the input voltage changes, still our output voltage need to be all the time constant. So voltage regulations here we can see here 5 volt it's regulating, here 9 volt, 15 volt, 20 volt, and also load percentage. Okay, and different line it's given. Then no load power consumption. That other term which we use is the standby power. Standby power means when you connect it to the input, but you are not connecting the load, then how much amount of power it's consuming. So we can see that at 90 volt AC, we are consuming 90 milliwatt, 19 milliwatt, 115 23 milliwatt, 230 30 milliwatt, and high line 264 worst case 33 milliwatt. So this is very good, very less standby power consumption. Then you will get the efficiency data at different line and different specs, and you can see the standard efficiency standard what we need to pass. Here it's written DOE 6, then COC version 5 tier 2. Pass fail criteria is mentioned, and yeah. So this is all about efficiency. Efficiency measurement need to be taken at 0%, 10%, 25%, 50%, 75%, and 100%. Then at a worst condition, different line, what is low line, high line, each which are the basically critical component on the board or the component which are giving you the highest temperature. This is the measurement taken using the thermal camera. You can see that the temperature on each component, and accordingly it's a low line, high line temperature mentioned. So if I particularly highlight the device, so we can see that at low line it's going the max temperature of 85 degrees Celsius, and at high line it goes to the 89 degrees Celsius. And apart from that, one more thing, you can see that the AC bridge that rectifier going to the highest temperature. So generally solution to this kind of thing is to use two bridge rectifier in parallel such that you can divide the current and hence bring the temperature on this AC bridge direct bridge rectifier down. Or also you can do is to use the two hole component instead of the SMD. So that's also help to reduce the temperature on the board, because what happen if we are having the SMD component, then all the temperature directly get reflected on your board. So, but in through hole it get in contact with the air, so it reduces the temperature all across the board. Then here are the EMI test report available. So in the industry level, there are two type of classification, non-commercial and commercial. So this comes in the category of the non-commercials, and automotive things comes in the category of commercial. So in the non-commercial, we have to pass the standard called CISPR 32, in which you have to do your both test, conducted EMI test and radiated EMI test. In the conducted EMI test, this is the standard. Basically, this is class B, CISPR 32 only, but there is with different reason, the name is changed only EN 55022B, but both are having the same standard. Here, two measurement, average as well as quasi peak. Measurement have been taken, and it's here you can see that it's failing 1 point. Actually passing, not failing, but here is with respect to its quasi peak. And the spectrum which you need to 150 kilohertz to all the way 30 megahertz. This is your standard requirement. At different input and output level, EMI test report is available. Then another thing is the startup and shutdown waveforms. So as this is a USB PD application, when you are supplying, so by default USB PD start at 5 volt, and if you need 20 volt, then it communicate with the device and uh, change the output level accordingly. So this is what's shown here. You can go through the details. Same things here also. Yeah, here I want to give slightly time. So I was discussing, we'll go back to the PPT. So I was saying that at the light load conditions, we are operating in the burst mode. Then lighter load, we are operating in the frequency foldback mode. Frequency foldback, then light valley switching in between, like SIC all the way second to SIC, and the heavy load we will operate in first valley, and the peak power demand we will go into the CCM. Let's see what's happening in this design. So this is had been taken at a low line, and we can see the output voltage here 20 volt and full load, which means 20 volt and 3 ampere means 60 watt. So we can see that it's operating in the first valley. This is the switch node operation. So if I go to the second one here at a high line, full load only. So at a high line, it's operating in the third value. So that's what I wanted to highlight when we are talking about the calculation for the bulk cap, that it done at the minimum voltage and full power. So we have done our assumptions while calculation that the minimum voltage and full power, it should operate in first valley. This is what happening here. So if you go to the higher voltage and it's operating in third valley, which means that still you have a capability to support more power, higher power. So this is the advantage, not a disadvantage. And then we can see that different input voltages they are showing. So here switching frequency also mentioned here, it's switching for 125 kilohertz. Here it's 75% load, it's switching as 133 kilohertz. 230 voltage. So the lower the power, here frequency. So we can see that here the curve black one. When we are a higher power, our frequency will come down. So here we are seeing it's a 125 kilohertz, but at this point somewhere here it's operating, and there it's a 133 kilohertz. So then it's a 75% it's operating in third valley, 50% if we are going down to the power, we can see it's operating in the fourth valley. We are going basically in this direction. And then is 25% it goes into the seventh valley, 3 seventh valley, then it goes into um, it's stop now it's turning into the frequency foldback mode. All the way from 6 to 7, these two are in the frequency foldback mode, and then it's come into the burst mode. So in the burst modes, a minimum 3 packet of switching frequency will appear, and based upon the output voltage, next switching cycle or switching pulse will come. Same thing discussed in this at different voltage, input voltage. And then here they are talking about the voltage stress across the primary FET, which is inside the device. So here it's clearly mentioned that at the maximum input voltage and maximum power, as well as so maximum voltage stress, you can see 640 volt. And this at this point. So this is here they have the voltage of almost 642, less than 560 volt. This side we can see 502 volt. So here is max voltage 502, recommended to have less than 560 volt, and here max voltage is 640. So it's in the safe operating range. And then X-cap discharge, which I have already discussed, same waveform last time. And then ripple and noise. So the ripple measurement here, I would like to highlight one thing. So what happened when we do the ripple measurement? Generally, that time lot of extra noise get coupled, and you will see a very noisy waveform sometimes. Like completely, you will see like this. Okay, let me redraw. So what happened when it comes like this? After this, you will see a lot of spikes. So there was a measurement technique. What we do generally, sorry, it will go straight basically. So what we do for that kind of things, when you are measuring the ripple noise, put a probe. On the probe itself, you can put something called epsilon capacitor. So those caps have especially very less ESL and less ESR, thus helps to reduce your uh, give a correct measurement basically. Extra noise it suppressed it. And this ripple and noise is basically coming due to the ESR of the output cap, and it's very low. And there are the standard which we need to pass it. Then next things come low transient and line transient. So in the low transient, what does it mean? Low transient means when we are giving the pulsating load. So what is the overshoot and undershoot max values it's allowed? So when we go from all the way low current to So when we go from all the way low current to high current, so what happened? Let's say our V out is regulating. Suddenly we demanded more power. So what happened? Our V out slightly take a dip and then again it start regulating back. So this is called undershoot. And what is the max value it can go? That is depend upon the how much power level you are doing. So we go all the way from let's say 0 to 100%. So your overshoot should not go, undershoot should not go so much high value. For example, if it's operating at 5 volt, so it should come till 5.5 volt, not more than that. Sorry, 4.95. Sorry. And when you come back again, like here and 0, then it will take a overshoot and again regulate back. So this should not go above 5.5 volt. So this is called load transient. And here, like it had been taken this, I think, 10 kilohertz. So that's why, yeah, this is 10 kilohertz load frequency. That's why you are seeing not, it's, you're not basically able to see how it's going back. So the waveform capture is in this duration only. Then over current protection. So basically here, max current is supporting 3.46 ampere, different voltage output for what the max current it can support, or else it's triggering the false, and at the CDX pin, they are able to measure it. So these are the signals you already get. Yeah. So this is all from my side. Uh, if anyone have any question, please you can ask.
If you, dear participant, is there any queries? Please let us. Any queries? Okay. Is there any queries?
Yes, may I ask one question, please?
Yes,
Um,
yes,
Sure.
please go ahead.
yes, actually, most of the cases you were used that adapter for charging, is it? These are the charging for electrical vehicle only? Hello,
Yes, no, ma'am. These are the mobile phone chargers.
only mobile phone because 65 watt also is there. Uh, so these are the mobile phone only, the big one. Hello.
Okay. Yes, yes, yes. Ma'am, just to clarify, you are
Uh-huh.
talking about these things, right? This one.
Yes.
So this is
So
basically adapter for the laptop. But in the electrical vehicle, we generally prefer a higher power, greater than like 750, greater than 240 watt, right? So that side we use the LLC topology, not the QR flyback. So here I'm talking mobile phone chargers, laptop phone chargers.
okay, only for that. And it is always the adapter is from AC as usual. Okay,
Yes,
as
correct.
usual. Normally AC is, but there is any scope for DC to DC charger?
Yes,
Because there
yes.
are so many DC microgrids are available now. So in Texas Instrument, there is any DC to DC charger adapter kind of thing?
Okay, so here are two things. First thing, DC-DC charges can be made, especially if you see in this particular slide, I told that there are some advanced circuitry. So in this advanced electrical socket, what they do the AC to DC rectification inside, and you will ended up with the DC output voltage, and thus you can connect your charger, and you can for the same things here can be used as a same UCC 28826 can be used as a DC-DC charger. Now coming back to electrical vehicles, yes, we do have a DC-DC chargers in the electrical vehicle side, but if you need particular some reference design kind of things, so please drop the mail to my mail ID, then I can share it.
Yes, that is actually we have money. We require this kind of because we have the DC microgrid. Okay, and we want to make the charger for mobile as well as for electrical vehicle, and it can be tested if there is any charger for evaluation purpose. You are talking about, so
Mhm.
that can be possible if you have that kind of charger. So may I get one your mail ID, please?
Yes, ma'am. Yes, ma'am. Sure.
Okay. Okay, thank you. That is the question. Okay.
Okay, I think I should have kept my mail ID somewhere on PPT, but yeah, I will drop it here for now so that you can copy it.
Okay.
Ma'am, here one more request. What you can do if you want the this evaluation design which I have shown to get it evaluated, you can directly either purchase from the ti.com or like reach out to the salesperson, those kind of things, and get the board and start evaluating. And in evaluation side, if you need any help, then I can support there.
Okay. Actually, from the West Bengal, really it is staff from TI site when we are going to purchase. Okay, but the thing is, if we are going through DigiKey or Robu, then we are getting that kind of purchase. But TI, we want to purchase directly from TI. So in that case, we are somehow we are not able to reach there to directly to talk to TI people.
Okay, okay. So, ma'am, for that kind of things, I would recommend you there. We have a something called E2E forum. You can post your query there. Some whatever part number related it is, the contact. Person who is responsible for that will get back to you within 24 hours.
Okay. Okay.
That is
Thank you.
E2E, e2e.ti.com. You can search.
E2ETI.com.
Yes, ma'am.
Okay.
Ma'am, I want to ask one question.
Mm.
Yes,
For
yes.
initial slides, I was not there. I was joined little late. Ma'am, actually,
Yes.
if I compare with other technology, how much is the GAN penetration in this kind of like are they available right now in the market in Indian market? Like how much percentage they have replaced previous technology?
Okay. So with particular GAN percentage, I don't have data on that side. But as far we talk about in Indian market, in particularly adapter, so yes, it's replacing almost most of the designs. In the designs, GAN is the future right now. So going forward, as the GAN allows you to go for the higher switching frequency with by default ZVS, right? So GAN is the future, and percentage wise at present I don't have data, but I do know that it's already available in Indian market.
Okay,
And
ma'am. Thank you.
one power optimizer I have seen also in Texas Instrument. That is also, I think, available now, and that is also GAN based.
Ma'am, may I know regarding what you are talking? I mean, power optimizer, any
Optimizer,
part
that is
number?
part number I cannot remember. I once see, but I
Okay.
cannot see it in the market. Is it only demonstration, or the market? It is available in the market also. That is
Ma'am,
my power optimizer, GAN based.
ma'am, I cannot say. I mean, till the time I do not know the part number, because in Power Optimizer we have a very broad portfolio. So it's tough to say whether it's right now in market or it's just as a reference design on the TI.com. So I cannot say much on that side. But yeah, in the
Okay.
GAN, lot of there are GAN product already available in the market.
Okay. In Texas Instruments
Yes,
product.
yes, yes, yes.
Okay. So actually,
This
there are the students, if they are interested to do some project or another, this kind of tech TI product evaluation, that is, there is any scope for internship or kind of thing, so that uh, if any possibility for that.
Ma'am, this is kind of like already I myself been 1 year intern at the TI in the TI, so they already goes for hiring in the Texas Instrument as per my knowledge.
Okay.
There is a
From the
scope.
university or any kind of institute, that means students or the
Actually,
PhD
madam,
students. Mm.
hello, ma'am. Actually, in that case, the TPO directly they are contacting. Okay, so TPO
Yes.
need to be contact to the TI.
Yes.
So from your training and placement cell, so they may be then they may be conduct the placement drive or internship drive to your institute. Okay. So
Okay.
is there any other question?
Yes, sir, I have one question. Madam, how
Okay.
much maximum power rating can go with flyback convert? Maximum power rating.
So I have seen the customer demand till 150 watt. But it's depend upon what is your trade-off, what is your requirement. Like, are you looking for size, looking for cost, or efficiency? So till still you can go till 150 watt. Based upon your demand, you may go into the different topology also, but still QR flyback is preferable. With
But
respect to
if I want a 500 watt rating, is it possible from flyback to account with 500 watt?
500 watt.
Uh,
No, no, not recommended at all. So you will not have a good efficiency. Efficiency challenge will be there. So for 500 watt, a very good choice is the LLC converter. In a very high power density, good efficiency.
okay, ma'am. Thank you.
Okay. If I think we have to go for the next session. Okay. Is there any other queries? I think no queries. Okay, thank you, Anita. So giving your really precious time to us. Okay,
Thank you,
so
sir, for giving me this opportunity. And thank you, everyone, for attending it.
yes, I think it's a very good opportunity from our side also, because we are learn a lot of things from your presentation. Okay, I think our esteemed participants, they are also getting a lot of idea and product idea, as well as some uh, experimental aspects. Okay, idea from the using the devices and all those things they can able to know. Thank you again. Okay.
Thank you, sir. Thank you, everyone. I hope this given you a kind of clear idea what's going in at the industry level.
Very good.
Thank you, everyone. I will drop it.
Okay, welcome.
Thank you, sir. Thank you so much.
Okay, okay, welcome. Thank you. Bye.
Bye, sir.